Everybody should have a card. True or false? Everybody should have only one card. If everybody has only one card, then everybody has a card. Okay, in your hands, you have either a metal or a non-metal. Which means that as we make our ionic compounds, if you're a non-metal, you need to find a metal to make a compound with. And if you're a metal, you need to find a non-metal to make a compound with. Now, one catch. You do not represent one atom of that element. You could represent two atoms of that element. You're either one or two atoms of that element, and you need to go and make as many compounds as you can. Let's see how it works. As you come up with a compound, we'll go ahead and write them on the board. You can get up out of your seats if you need to, but I don't know. I'm a metal. No. What? Has anybody made a compound yet? Has anybody found a pair? Are you guys? Okay, so we've got a, well, who's the metal?
I'm the metal.
You're the metal, so you go first, and you're the non-metal. Okay, we've got rubidium chloride. Go find another. Anybody else?
Potassium oxide.
Really?
Just kidding.
What would it be? What would your formula be? No, I'm not saying you're wrong. You could be right. I'm not going to give you the answer. When you have your formula, let me know. Barium iodide?
That is very much a metal there. Yeah, it's a metal. CA is a metal. Good one, Eric. I'm a metal.
Derek, come be my metal.
I'm a metal. You're a metal and somebody else is a metal.
Cesium bromide, okay?
Me and Stephen are now metals.
Now, if you're supposed to be a subscript 2, let me know. Okay? You're saying the potassium oxide? Is that what that is?
Say yes.
Oh, okay. We'll keep moving then. Somebody else? Calcium chloride.
Who's a non-metal?
Potassium oxide.
Potassium oxide? KO? Oh, you see, yeah, two metals. You guys don't. You guys need to stay way, way far apart.
Somebody be my friend. Me and Starnes.
Rubidium. What is that?
Potassium.
Strontium chloride?
I can't even pronounce it.
Potassium chloride.
Somebody be friends with me.
He's a metal.
Are you a metal? I think this is right. I don't know. Who's a non-metal? I have
We
another
got rubidium.
Well, okay, so the metal is cesium. You're saying it's CSO, that's a compound? Okay. Potassium iodide? Ki?
Rubidium bromide.
Barium chloride.
Look at first. Oh, Stephen. Rubidium oxide.
Potassium bromide.
Rubidium oxide.
Rubidium oxide. That's your okay. Oh, by the way, just because I'm writing it on the board doesn't mean it's right. But I'm just writing what you're telling me you are.
Who's K? Who's been around? Molly, go figure.
Strontium bromide. And I'm assuming it's a 1-to-1 unless you tell me otherwise. Oh, by the way, they're not all 1-to-1. Calcium iodide. Okay.
Ooh, the mouse is on my card.
Cesium chloride.
Which one?
So far, everyone is a 1-to-1. Okay, so from the back, bromide. Those are two metals, aren't they?
No, mine's not.
Okay, so what are you saying? Calcium bromide? Okay. And barium oxide? And rubidium iodide.
Okay, I've been.
Is there another one? Anybody else? Barium bromide? I've got a habit of doing uppercase blocks, so it's not. Okay. Anybody else? Gonna stop at that one? Let's look at what we've got so far. We have the metals. Let me know if I miss you, but potassium, rubidium, cesium, calcium, strontium, and barium, right? Who is potassium?
Me.
What is your ionic charge?
What?
Okay. When you form your cation, what column are you in, Miss Potassium? Column 1. So when you become an ion, what charge do you have? You have 1 valence electron. Do you want to get 7 or get rid of 1? You want to get rid of 1, right? When you get rid of 1 negative, you become, believe it or not, you become positive. Believe it or not, Molly becomes positive. Okay, so potassium is a +1. Rubidium, who are you?
Me.
Hey!
Hey.
What's your charge?
1.
Okay, you sound very confident there, but okay, 1. Cesium? +1, okay. Calcium? 2 positive, okay. We're going to do 2 plus that way. Strontium? 2 positive. Are you positive? Yes, you're positive, you're 2 positive. And barium? 2 positive. You are way too positive. Okay, so potassium, rubidium, cesium, calcium. Okay, so you see that these would be, without being too geeky, column 1 and column 2 elements, right? Yes. All right, now, nonmetals. We have iodine, chlorine, bromine, oxygen, carbon. See, argon, chlorine. I may have dropped carbon because of space. Okay. Yeah, because I was trying to figure out if she was going to be testing or not, and I needed one for her, you know, stuff like that. So, are there any not represented up here? 1, 2, 3, 4, 5, 6, 6 and 4. Okay. Right. So, iodine. 1 negative. Chlorine? 1 negative. Bromine? Are you positive?
I'm not that positive.
You're not positive. Right, you're negative. Okay. So, bromine, you are in column 7, which means, no, 1 negative because you want to have 8. Okay. Oxygen?
2 negative.
Correct. 2 negative. Good. All right. Now let's look at, and I'm not going to go through all the pairs there could be. Let's just look at the ones that you suggested. Okay. Cesium bromide. CSBr. Every one up here is a 1-to-1, right? Which means that every one of these molecules is balanced charges, right? You've said that these relationships are what you're forming. And so there's as many positives as there are negatives in every combination. That's what makes an ionic compound balanced. Okay? So that would mean that cesium with a +1 and bromine with a -1 equal but opposite charges. Okay. Cesium oxide. Okay, cesium with 1 positive and oxygen with 2 negatives. Is that right? Not balanced, is it? How do I balance it between these two? If cesium has a +1 and oxygen has a -2, how do I get a balanced charge? Please, make me feel competent as a teacher. Give me an answer. Even if it's wrong, give me something. And it doesn't involve the speed of light, okay?
Oh.
Do you switch the superscripts and make them subscripts?
That's the concept. So what would this formula become? CS2 oxide. It's still cesium oxide. It's pronounced that way. But cesium and oxygen can only come together in that combination because that's the formula that gives a neutral charge, net zero charge. 2 1 positives makes 2 positive, and 1 2 negative is 2 negative. Opposite and equal charges, boom, It's balanced. So it's a cesium oxide is CS2O. Third one, cesium chloride. We have a +1 and a -1. Is it balanced? Rubidium chloride. Rb +1, Cl -1. Yep. Rubidium bromide. 1, 1. Rubidium oxide. Oh. Oxygen, you just don't understand your worth. That's the problem. Okay. Oxygen is worth -2. And that's not negative when it's -2. You're worth 2 in negative currency. We're looking for 2 in positive currency to balance you out. So if oxygen is going to match with rubidium, what is rubidium? How many do we need? We need 2 of them. Do you get the trend here? Guess what? When you see oxygens, and if the metal goes to a +1, you need 2 of them to balance out the -2. So rubidium iodide, are they matched? Yep, they're matched. And 2 positive and barium, you're underselling yourself, right? You should expect iodine to kick in 2, right? You need 2 because they're only giving you 1. You need 2 to match your 2. So it's barium iodide is a BaI2. What about barium chloride? 2, 1. Man, barium's getting ripped off here. Barium oxide. Guess what? Cha-ching. +2, -2, match. Okay, was this the 2 ladies right there? I thought, okay, I was going to. So, anyway, barium bromide. Is it right? No. How do we make it right? You need 2 bromide, yeah. Because barium again, underselling. Let's go on to calcium. You said calcium chloride. Right? I can do sound effects. How do we make it right? Does everybody see it's CaCl2? Because calcium has a +2, I need a -2. I only get -1 from each one, so I need 2 of them to get -2. Now it's balanced. Calcium iodide, is it right? I get the impression calcium undersold themselves again as another element. So it's Ca what? I2 and CaBr2. Potassium oxide, is it right? No, it's not right?
No.
Miss Potassium, what should it be?
K subscript 2.
See, you're overselling yourself now. You should be, K subscript 2. You got to give up 2 to match the 1. Your oxygen, right? To match the 1 oxygen. KCl, is that right? Yes. Ki. Yes. KBr. Okay. Now, just so you know, there's like 3 times as many possible combinations than you have up here. So there's lots of options. SRCl. Right or wrong? Wrong. Who undersold themselves? Strontium. Strontium, you're carrying a +2 charge. -1 for chlorine, so we need a what? What's the formula? SrCl2. Strontium bromide, is it correct? No. Same reason, right? Because bromine has a -1, strontium +2, you need 2 to 1 to make it balanced. Okay, get the idea, again, refresh this idea of how do we make ionic compounds? We're going to combine the metal and the nonmetal in their ionic form, and the net charge is going to be balanced. And we do that, the shortcut when we write it is like you reminded us, is to take the superscripts, which is the charges, eliminate the charge sign, and then transpose and cross them, bring them down below. That's a shortcut to write the molecule. For example, if we do that for the strontium bromide, we had SrBr. If we put the charges, strontium is a 2+ and bromine is a 1- like that. We eliminate the negative and the positive, and we bring those down as subscripts. So it becomes SrBr2. And what we're doing is balancing the charges. That's what that shortcut does. It balances the charges. So any questions on that review? We're good? Okay. I am going to erase the board for a moment because I do have a couple slides we're going to use today, and then we'll be back to whiteboard quickly. Hopefully in the near future we won't be using whiteboard, we'll be using smartboard. And if once that thing is fully set up and working, I should be able to record a video of the smartboard and put that on the video as well. So we'll have, rather than having the whiteboard, I can transition from the whiteboard to the smartboard on the video, and you'll get both content all the time. So that should be sweet. For those of you watching at home, I apologize, we're not going to be there right away. We may leave the camera there for today. I may try recentering it. One of the problems is when I bring it centered, you can see the board much more clearly, but you get a lot more light bounce back from the front, from the camera. It kind of washes it out. So I may leave it there for today and see how it looks on the video when I'm done. All right. Let me check. No, you can have them. It's your identity, right? It's who you are. Actually, I'm not going to be able to check it without shutting it down, and I don't want to do that. So, yeah. Who am I? And then say, hey, tell me the truth. Am I negative or positive? How do I seem to you? Are you a metal or a non-metal? And do I attract you or repulse you? So what am I? You start asking questions like that. What's that? I need to see your ID, and you pull out the card? Yeah, right. All right. We're going to do a quick review of some of the periodic properties we covered last time I was in here. So what does it mean if something is a periodic property? We looked at the periodic table, right? And a periodic property is something that we can discern. It's a relationship. It's a trend. It's something that we can discern by looking at the periodic table. What the term actually means is something that repeats itself. Okay? Something that happens, and it's a pattern that repeats itself. That's what periodic means. So the periodic property in chemistry is when we look at the periodic table, we can see general trends, the way things relate to one another. Two elements, if you're comparing two elements, there's a direction of a trend. And if you're just comparing the two, you can say which one is greater than or which one is less than based upon the trending. We get that from periodic property. First periodic property we're going to talk about is ionization energy, but before that we need to talk about ionization. Somebody give me just a real quick, doesn't have to be from the notes, technical, but what is ionization? What does the term ionization describe? Yes, ma'am?
An atom turns into an ion by losing.
Right. You gain or lose an electron, and by doing that, you become an ion, and that's called ionization. Taking a neutral atom, which means that protons and electrons are in perfect balance, and then creating from that an ion means gaining or losing electrons. Remember, you can't gain or lose protons, because if you do, you're now looking at a different element. You can gain or lose neutrons, but we're not going there right now. That's kind of outside the scope of our class. But we freely and always gain and lose electrons, because ultimately a chemical reaction, how one piece of matter relates to another piece of matter, is based upon the electrons. And more specifically, which electrons? Vocabulary word begins with a V. It's not viceroy, it's valence, right, your valence electrons. So as two atoms come in proximity to one another, the way they're going to act or interact is based upon the valence electrons of both atoms. So it's going to be a relationship between the electrons. We're going to get into that much more heavily today. Okay. So that's what ionization is the process of making an ion, which is more or less electrons than protons, giving it a positive or negative charge. So the ionization energy. Now the way I asked you to look at this from the perspective of the atom that has the electrons. So describe to me what ionization energy is from the perspective of the atom who has the electrons in question. Do you remember? What's the example I gave?
It was if Zach and Molly both want something, Molly has a thing and she wants it, Zach wants it more. How much energy does Zach need to take it away just a little bit more?
Right. So in that analogy, I said two people have something. One person is holding on to something because they want it. Another one is going to be taking and trying to pull that something away. And in that example are both two of the periodic properties we're talking about. The first one, ionization energy, in that example is the person who has the thing. In this case, the electrons. The atom that has the electrons that are in question, how much energy does that atom use to hold on to what they have? That's the ionization energy. Oh, by the way, that same amount of energy is what the other atom would need to exert in order to take, or technically just a smidgen, which is a very technical term, I know, just a smidgen more. So in that case, if Molly's holding onto something and Zach wants it, Zach would have to pull it away from her with a little more force than Molly has holding onto it. But ionization energy, you could think of it as the amount of energy that Molly uses to hold onto it. Okay, and how does that periodic property look? If we were to imagine a periodic table, what would that trend look like, that periodic property trend look like? Go ahead.
To the right now.
Up and to the right, right? So if you think about ionization energy and you're looking at a periodic table and you're comparing two different atoms, you say, which one has a greater ionization energy? Well, the one that has the greatest ionization energy is the one that is farther up and to the right in that trend. So if Zach is stronger than Molly in terms of, well, let's put it this way. If Molly is not as strong as Zach, that's because we're looking at it from the perspective of the one that has the electrons. If Molly's not as strong as Zach, if they were elements, we'd expect Molly to be lower and to the left of Zach to be higher and to the right. Because Molly is trying to hold on to something, but we know that she's eventually going to lose it because Zach's going to take it from her, which means she doesn't have as much, let's say, ionization. Actually, the technical way to say that would be that there is a couple of other atoms. Zach is attacking Molly, then Zach is attacking somebody else, and he's which of those two other people he's attacking has a greater ionization energy. But you kind of get the analogy, right? Eventually, all analogies break down. But you would expect that ionization energy, as you look at two different things, as we go up and to the right, those atoms are holding onto their electrons tighter or stronger. So if some piranha comes in the area, Zach, you're now the piranha, you come in the area just trolling for electrons, you're going to look for the weakest link, right? So you're going to look low and to the left because, man, you can go there and pick those things off easy. The higher and to the right you get, the more work you're going to have to do to get them, the more they're going to fight. Okay? Questions on ionization energy or the trend, the periodic trend? Electronegativity. That compares to ionization how? Well, in the analogy, we said Molly is holding onto the electrons, and she's using a certain amount of force to hold onto them, so that's the ionization energy. And then comes along Zach, and Zach decides he's going to take the electrons. And electronegativity is the amount of energy that Zach is going to use to take the electrons. So that's the deal where if Zach wants to take them and uses more force to take them than Molly uses to hold on to them, guess what happens? The electron goes to Zach. Zach then becomes negative because he's taken Molly's electron, and Molly becomes positive because she's lost an electron. That's happening because the electronegativity of Zach is greater than the ionization energy needed to take the electron from Molly. Okay? And what is the trend for electronegativity? It's the same thing. It's the same trend. And when I shorthand this in my notes, I have a periodic table and I have an arrow this way, and that upward to the right arrow says IE and EN. Ionization energy and electronegativity trends up and to the right. So in the same way as we compare two atoms, we can compare their electronegativity, we can also compare their ionization energy, and whichever one has a greater ionization energy is also going to have a higher electronegativity. And think about it. That makes sense, doesn't it? The more an atom wants to get electrons, the more it also wants to keep what it already has. You see the connection? The more it wants to get, the more it wants to keep what it has. Because it makes no sense for, let's think, again, we're personifying this, but if an atom were to go out and be on the hunt for new electrons, it wouldn't make sense for it to be easily dropping the electrons it already has if it's on the hunt for more. It's going to get some, it's going to hold onto them firmly, and it's going to hunt for more while it also holds onto what it already has firmly. If you're a metal, you don't have to be convinced. You're trying to give these things away. Okay? So you're not going to hold on to it very hard at all. And oh, by the way, if somebody comes up and offers you one, you're not going to take it because you're trying to get rid of them. So it's kind of in one of those games where there's a game where you know, if you try to get rid of cards, but you're trying to get cards, you want to get certain cards, you want to get rid of other cards, and people offer you a card that you don't want, you don't take it. You say, I'm not looking for that card. As a matter of fact, I'm trying to get rid of that suit, or I'm trying to get rid of that number, whatever the case may be. That's kind of what's happening here. Those atoms that want to steal electrons also want to hold on to what they already have and not give any up. Because it's kind of like if I gain one, yes?
Lindsay's on her way back to class.
Thank you, ma'am. All right. So the more an atom wants to hold, the more the atom wants to get and is willing to use force to get, the more it's going to use force to keep. The last trend we had was atomic radius. And it did say that this one is a little bit counterintuitive at points. Right? What's the trend for atomic radius? Back. Down and to the left. It's the opposite direction. And remember we said it's kind of counterintuitive. I mean, it makes sense that as you go from the top of the periodic table to the bottom of the periodic table, that the radius of an atom would get larger because you're adding electrons. You're adding energy levels, actually. Okay, go ahead. Trying to avoid have to edit your face out of the video. So if you guys do that, if you come through and pass the camera so your face isn't in the camera, I'd appreciate it. That way I don't have to go back and do all the clipping and all that kind of stuff. Do the fuzzy thing, like, who's that blurred out person in there, and do all the investigation. So as you're going from top to bottom on the periodic table, it makes sense that you're first energy level, second energy level, third energy level, fourth energy level, fifth energy level, so on. Okay? What doesn't seem to make sense is as I add electrons going across, that the radius actually gets smaller. But remember, the radius gets smaller because we're not adding energy levels. We're adding electrons into the energy levels that we already have. And when we do that, we're adding more positive into the nucleus, which means it pulls in the electrons even firmer, right? They're not going into higher energy levels. So as we add more centralized positives, they kind of pull all the electrons in until suddenly, boop, new energy level. So as soon as we go all the way across the periodic table to column 8, as we go from as we're going across an energy level, the radius goes down. And then suddenly we need to add one more to go to the next energy level, which means we come all the way back over to column 1 and add the S1 electron. Suddenly, boop, because it popped out a new energy level. And then as we move from left to right, boop, so looking left to right, it's getting smaller. As we look top to bottom, it gets bigger. With that, we're moving on to covalent compounds. And a few things we want to compare and contrast between ionic and covalent compounds so we understand the differences. Because the key is the difference. It is two fundamentally different ways of making a compound. The exercise we did at the beginning of class was making the ionic compounds based on the electron charges, based upon the concept of, well, first of all, meeting the octet rule by a give and take relationship. Those of you that were metals, you had given up electrons to become positive. Those of you that were nonmetals, you had gained electrons to become negative. And now you're just out there doing combinations to get zero charges. So ionic compounds are formed by meeting the octet rule through giving and taking of electrons. Remember, the metal gives up an electron to the nonmetal. The nonmetal becomes negatively charged. The metal becomes positively charged, and they form the molecule by electromagnetic attraction. The opposite charges cause them to come together. Think of magnets. Two magnets, they have a charge, they come stick together. That is what's happening when you have a metal, nonmetal, and they're both ions, opposite charges, they come together like magnets. Same electromagnetic attraction. You can think of them as magnets being attracted to one another, and guess what? When they come together, they're now a molecule. A sodium +1, a chlorine -1, a chloride, sodium chloride. But the bond between them, that attractive force, is relatively weak, which is why when we put it in water and mix it up, they separate and float around. They're now singles on their own again. We take the water out, they come back together. Okay? Now, we're going to start talking about covalent compounds. And you learned the ionic naming paradigm and the covalent naming paradigm because we said that there's a fundamental difference. Remember, ionics can only form in one combination. We did that exercise again to show you there's only one way that they can form between two elements. When we get to covalent compounds, we're now talking about I can form multiple compounds with 2 elements. The rules are different because covalent compounds meet the octet rule by sharing electrons. They share. They don't take and they don't give, they share. It's a big old kumbaya, can't we all just get along? We're just going to share everything together, okay? And later on we'll talk about the sharing. It's not fair sharing, by the way. They share, but sometimes one element's a bully. And I use the analogy of buying a car together, like you and a friend go out and buy a car together. And part of the agreement is, okay, you both own the car and you can use it whenever you want, but your friend gets to have it Friday night and it stays at their house over the weekend, but you both own it. But they get it whenever they want it. That kind of relationship actually happens between atoms too. But for now, we're just going to talk about sharing. Not giving and taking, sharing. So the electrons that are shared, it's not that they don't belong to one and they don't belong to the other, it's that they belong to both. And those sharings form compounds through bonding. When you have an electron pair, is what they're called. Because if we're sharing, I'm an atom and you're an atom, and we both need one more electron, and neither one of us is willing to give it up because we have high electronegativity, and we have high ionization energies is what it is. I'm not willing to give it up, and I'm willing to fight to get another one. And let's say I used Zach before. Zach and I get together, and I say, Zach, I need one more electron. I'm not giving up any, and I want yours. And Zach says, well, Mr. Baker, guess what? I want your electron, and I'm not giving up any. And we finally come together and say, you know what? As unseemly as it may be, we're going to share one. I'll share one and you share one. Okay? So if you needed one and I share mine with you, you think you've got all you need. And if I need one and I share yours with me, guess what? Now I've got all that I need. We haven't added or taken any electrons away, but we're sharing it, and it technically belongs to both of us, not to either of us. That is what we call a bond. And we'll show you what that looks like in a diagram. But here's the other thing I want you to always remember. We'll call it a bond. When you think of bond, most people think of like glue. 2 things are bonded together. Remember, even though they're bonded, they still never actually touch each other. We're talking about forces in the nothing space between somethings. Okay? So when I say that 2 electrons form a bond, that's just a way of us to understand that they aren't going to give up their electron. They're willing to share it, but they're not going to give it up, which means when it becomes time, like we mix it in water, water is, and we'll explain how that works later, but water is strong enough to separate 2 ions. It can overcome that magnetic attraction. But water's not strong enough to break a bond, because it's kind of like, you know, in that analogy, I'm holding on, maybe I've got my hand holding on to Zach's belt, and Zach's got his hand holding on my belt because he doesn't want to give up the electron he's sharing with me. And he's not going to let go of the one I'm sharing with him. And so we go through things a lot tighter together. We don't give up. And we call that a bond because it appears like we're stuck together and we can't come apart. But again, physically speaking, we're smaller. There's no matter between us. So it ultimately comes down to forces, just like ionic forces, but they're different. So let's take a little bit a look at, and the very first covalent molecules we're going to look at are what are called the homonuclear diatomic molecules. This is so important. You know, occasionally at the Naval Academy I'd have teachers that when they would say something very important, they would do something like this. Homonuclear diatomic molecules. Stamp their foot 2 times. Now that doesn't mean I'm Mr. Ed. What that means is, hey, you better have written this down in your notes, and you better understand this concept. And if you don't understand this concept, you better speak up, because this is one of those big deal critical things. Okay? Homonuclear diatomic. Let's look at the words, because we know chemistry is mostly about vocabulary. No, communication of concepts is about vocabulary, and chemistry communicates all the concepts. We need to understand the vocabulary. Homonuclear. 2 words in there. Homonuclear is a combination of what 2 words? Homo and nuclear, right? Homo means same. Nuclear, same nucleus, right? We're talking about molecules that have the same nucleus. Diatomic. Di is a prefix meaning 2. Homonuclear diatomic. I'm talking about something that is a molecule where they have a common type of nucleus, and there are 2 atoms that form the molecule. So the definition is elements that are made up of molecules rather than individual atoms. Elements, okay? This is where I said before. I said, now, when we write on the board, remember we're doing the problem, we say, okay, we have so many grams of hydrogen and so many grams of oxygen and so many grams of carbon, and I would write it on the board and I'd write, okay, now for now, I'm going to write 32.5 GO. Sometime in the future, we're going to talk about how this should actually be O2. Okay? This is the future. This is the conversation we've been holding off to talk about why it's O2, H2, N2, Cl2, and not simply O, H, N, and Cl. As a matter of fact, the examples here are, these are the homonuclear diatomics. You have to have these memorized. Matter of fact, they have to become so second nature that if I say, okay, we've got hydrogen gas, you're going to write down H2. Because all of these become all of those. What is this communicating to you? These are individual atoms. If I wrote N, O, Cl, F, Bri, At, or H, you would look at that and go, okay, that is one atom of each one of those elements. If I write down on paper N2, O2, Cl2, and so on, you look at that and go, okay, these are two atoms of that element come together to form a molecule, right? They formed a molecule. I'm not saying that I've got two atoms of nitrogen. I'm saying I've got one molecule of nitrogen that's made up of two nitrogen atoms. That's what the N2 communicates. Now here's the deal. Looking at the periodic table, I know it's a little bit farther away now that we're installing the smartboard, but if you look over here at the periodic table, let me go over to it. Let's look at where these elements are at. Again, it's quite a stretch now. Hopefully in the future we'll get this onto the smartboard. But we're looking at, okay, starting with N, N, O, F, Cl, Bri, At. Does anybody see a pattern there? So it's NO in column 7. Forms a 7, doesn't it? It forms a 7, and the base is the column 7. 7, 7. Oh, guess what? One more exception. Hydrogen. So it's the 7 based on 7th, or 7 on the 7th column, and hydrogen. So nitrogen, oxygen, then your column 7 elements, and then hydrogen. And so from now on, when you're writing down something that says we have so many liters of hydrogen gas, you would write down so many liters of H2. The reason for that is that doesn't mean that individual atoms of hydrogen don't exist. But what it means is whenever a hydrogen atom comes in proximity to another hydrogen atom, they form an H2 molecule. Whenever oxygen, one oxygen atom is floating out there, another oxygen atom is floating out there, they're individual atoms, but as soon as they find another oxygen, they form an O2 molecule. And so on for every other case here. So that doesn't mean there's never an individual atom, but if they ever come in proximity to another one just like them, another homonuclear, same nucleus, right? Same number of protons in the nucleus, they will form a diatomic molecule. Two atoms come together to form a diatomic all the time. Now, whenever you have nitrogen, let's say, for example, I say, give me a nitrogen, that doesn't make sense. Because we don't have the ability, you don't have the ability to give me one atom. You normally give me a sample, right? And if you give me a sample of nitrogen, guess what? All that nitrogen is next to nitrogen. So guess what? They've all formed molecules. This means in nature, as they normally occur, these elements are always in the molecular form. They're not in the individual atomic form. They're always in molecular form. So if you're dealing with nitrogen, oxygen, chlorine, fluorine, bromine, iodine, astatine, and hydrogen, you're dealing with molecules, not atoms. Molecules made up of two of the same atom, same element. Okay? So that's a homonuclear diatomic molecule. And it's something you've got to know, you've got to apply, you're going to mess it up. But something's just going to be, Mr. Baker, are you really going to take off because I did put H2? Absolutely, you've got to get this. This is crucial. Does anybody not get the point that I think this is really important? Is it a little minor thing right now in your mind? Probably. That's because you don't understand where we're going. It's a big deal. You've got to get this concept down. And you've got to not only get the concept down, you've got to start applying it. So when you see something, if I say, write down one hydrogen atom, you write down an H. But if I say, you've got so many liters of hydrogen. You should automatically be thinking, I've got H2. I've got molecules of hydrogen, and so on. Let's look at what I got next. Oh, let's talk about how does this happen. Now, we're going to look at the Lewis structures. Hopefully by now you recognize this as two Lewis structures of two fluorine atoms, right? Fluorine is a common column 7A element, has 7 valence electrons. And we follow the pattern of 2, 2, 2, and 1. And I know, yes, technically that should be centered, but that's another thing about PowerPoint. Sometimes it's really hard to get the thing centered, and it's much easier just to say, okay, I'll offset it. I know it's not technically right, but for speed this morning I said, okay, that'll work. Now, if we were thinking ionically, what would we think should happen here? If we're thinking ionically, which is not correct. But in this situation, fluorine's looking for another one, right? And this fluorine's looking for another one. If we're thinking ionically, we might say, well, you know what, maybe fluorine, this one gives up one, and that becomes an octet on its own. But see, now we've got two of the same. They both want to get equally strong. Is that right? Equally strongly? No. They both have the same force to hold on to what they have, the ionization energy, and they both have the same force to steal from their neighbor, electronegativity. They're a perfectly matched set of twins. They're perfectly matched. They're both holding their own as tight as they can, but it's exactly the same as the other. And they both are trying to steal from the other one at the same strength. So, rather than one giving up and the other one getting, I mean, that would happen if they weren't equally strength, right? But they are equally strength. So what ends up happening is they get a sharing relationship. Now what I'm going to do up here is show that I'm taking these 7 electrons on each one and I'm going to reorient them this way. Okay, see, I still have 7 each. All I've done is kind of taken my Lewis structure and turned it so that this electron is looking for a pair, isn't it? And this electron is looking for its pair. And so rather than saying 2, 2, 2, and 2, now it's 2, 2, 2, and 2. In the same way, the other fluorine atom has 2, 2, 2, and 2. And so when we look at this, if I ask you the question, how many electrons does this left fluorine see? How many does it think it owns? It thinks it owns 8. Is its octet rule satisfied? Yes. This atom now has a full octet. It's not looking to give away any. It's not looking to get any more. It's satisfied. It's reached its lowest energy. Octet rule is filled. Okay. Looking at the other, is it satisfied? Sure it is. Because it looks at its basket full of electrons and says, guess what? I've got 8 electrons too. I've got my 7, plus I'm sharing one from my neighbor. I got his. And the neighbor's saying, no, I got my 7, and I got one of his. So both atoms here recognize that they have their octets filled because they're sharing an electron pair. Each is sharing 1, and the net result is 2. Now, we started with 14 electrons. How many do we have now? Oh, we can't gain or lose any. We only have 14. So we haven't gained or lost any electrons. But we've been able to satisfy the octet rule for both. So what we do is whenever we have a pair of electrons that are being shared, these two that are technically viewed as belonging to both, we change our Lewis structure so that we no longer show that as 2 dots, but we show it as a bar. That bar represents a shared electron pair, and that is what we call a bond, an electron bond. A shared pair of electrons forms the bond, and the bond holds the 2 atoms together. So both of these fluorines were looking for one more. They found it through sharing, and they're not going to give it up. They're going to fight hard to keep it. And that's what we represent as the bond, that fighting to keep what they've got and not give it up. Okay? So it's not real, there's nothing mystical or magical about it. That bar represents 2 electrons. So if you count up the electrons around each atom, hopefully you see that it's 2, 2, 2, and 2. So the bar is worth 2. On this 2, 2, 2, and 2, they both see 8. They're both full octets.